Hi, this is a paper on expanded decomposition with almost optimal overhead. This is a joint work with Nikhil Bansal, Arun Jambulapati, and I am Tachapon Saranrak. Let me start by telling you what is expanders and expanded decomposition. So the informal goal of expanded decomposition is this. You want to remove a fewest number of edges from the graph so that each component after that deletion become an expander. The picture looks roughly like this. You remove these red edges, and now the rest of the components here looks very well connected. It's an expander. This expanded decomposition is extremely powerful and find many applications across TCS. This paper is gonna give you the first or most optimal expanded decomposition in polynomial time. Okay, so now the key object is expander. Let me tell you what it is. There are two different notions, cut expander and flow expander. Let me start with cut expander. When you have a graph and some parameter phi, I said that this graph is a phi cut expander. If for every cut S, the number of edges crossing this cut is at least phi times the smaller side of cut. So the bigger phi is, the more robustly connected the graph is. And I'm gonna say that the cut S is phi sparse of, S is phi sparse. If this inequality is false, that is, you have that the number of edges here is less than phi times the number of the size of the smaller side of the cut. Okay, let me give some example. When you have this graph, with like a two, which is like a two clicks connected by two edges, then this cut would be a phi sparse cut, where phi is something like 1 over root n, because the smaller side is root n. Okay. So this is a bad expander. It's not even like the expansion is something like below order of 1 over root n. It's not even like a 3 over root n expander. On the other hand, if you have a random graph, even when the max degree is constant, we can show that with high probability, this is going to be a great expander. The expansion is quite big. It's a constant cut expander. Yeah. By the way, everything in this talk would extend to the more general notion of expansion with respect to any node weighting A. Something like conductance or terminal expansion, but we omit this just to simplify notation. If you know about this, just know that everything extends. Okay, now this is a cut expander. Flow expander is something similar, but it captures the same intuition from the different perspective. I will not define it completely here. What we just need to know from this talk is that cut expander and flow expanders, they are almost equivalent, but flow expander can be stronger by log n factor. So flow expander are more useful in many routing problems. And what do I mean by almost equivalent? So I mean this. If you have any phi flow expander, it is also a phi cut expander with the same parameter phi. But now if you have any cut expander, well, we can say that it's also a flow expander, but the expansion parameter get worse by log n factor, may get worse by log n factor. So cut expansion can be weaker by log n factor. What we want is flow expander, and flow expanded decomposition is a bit stronger. So now I can tell you what is expanded decomposition. So a phi cut off flow expanded decomposition is just a cut edge, okay? Edge set C, such that when you look at G minus C, each component in G minus C is a phi cut off flow expander. So something like this graph. this is a C here, these edges. Okay. So when you delete it, every component looks like an expander. And the goal is to minimize the cut size C. So what do we know about this? So first, if you want a cut expanded decomposition where every component is a cut expander, a phi cut expander, we know that it's enough to just remove phi and log n edges to get so that every component is a phi cut expander. And this takes exponential time, but this is optimal. At least it's tight on some graph like hypercube. You may ask, can we improve this exponential runtime? So we can, but now we can get cut expanded decomposition like before, but the cut size now is worse by square root log n. How about flow expanded decomposition? We can get it too in polynomial time, but now the cut size is worse by log n factor. So this is log square instead of log n. By the way, we don't know how to improve this log square factor. Even if I allow to give you exponential time, we don't know how to improve this. So now our contribution is this. We show how to get flow expanded decomposition. Remember, this is a bit stronger than cut expanded decomposition, such that the number of cut edges is close to optimum, even is close to matching this optimal bound here. Okay? And it's near optimum up to sub polylogarithmic factor. The running time is polynomial too. So our contribution again is that it's just the near optimal trade-off for expanded decomposition. For cut expanded decomposition, it's the first polynomial time algorithm. For flow version, this is even the first existential result. Now I want to tell you a bit about the previous approach, why they suffer from, why they cannot get near optimal bound. This is the barrier for the cut and recurse approach. So let me tell you a bit about cut and recurse approach. That is how to actually get this algorithm here. Okay. Algorithm is very simple. You look at the graph G here, and if the graph itself is already an expander, you don't need to cut anything, just return. You're done. Otherwise, it's not a cut expander, which means that there must exist a phi sparse cut S. So you find this cut S, and then what you do, you just add the edges across the cut to your final output C. Then you just recurse on both sides of a cut. You might find more sparse cut on the S side and on the complement side. You keep continuing until you're done, which means that you cannot find any sparse cut anymore. So each component will be a phi expander after you are done. So which means the correctness is trivial. You get that each component in G minus C is a phi expander. Now you get this. What about the cut size here? We can bound it easily too. So when you find let's say you find a sparse cut here, what you do is that you just charge the number of edges on this cut to the smaller side of vertices. So for each vertex, each vertex will be charged by something like phi because of this is sparse cut by this inequality. So now, how many times each vertex can be charged? It's at most log n, because each vertex can be on the smaller side at most log n times, right? Every time it's on the smaller side, the graph shrinks by half. So it means that the total cut that we remove is at most the total charge. And what's the total charge? It's n, the number of nodes, times phi log n, which is the total charge per vertex. Okay, so that's how we get the bound of phi n log n. That's how you get this one. This is optimal, but it takes exponential time because to find this cut here, we don't know how to do it in polynomial time. What do we know in polynomial time is here. To get cut expanded decomposition in poly time, when the graph is not in this step, when the graph is not a phi cut expander, in poly time, we only know how to find a phi square root log n sparse cut. So, but this result in the worst bound here. Okay? You pay a bit more by square root log n factor in total. And we don't know how to improve this directly because it has been a big open problem whether you can improve this bound to get sparser cut, something like anything better than phi square root log n sparse cut in poly time. We don't know how to do this. If you can do it, it's a huge deal. Okay, that's how you get this bound here. Now, about flow expanded decomposition in polynomial time, we're just gonna replace this here by flow expander. And when the graph is not phi flow expander, that is, if it's a flow expander, then we are done. If it's not, what you know is that you can find a phi log n sparse cut in poly time. And because of this log n factor, you pay a bit more here, not log n, but log square. And here there is a bigger barrier. It's a structural barrier called flow cut gap, because a cut that is better than phi log n sparse might not even exist. Okay, it's not just you cannot find it fast, it might not even exist. So from here, you get log square. So you get some barrier here. So you can see that it's not clear at all how to improve this. Now let me tell you how do we improve it to near optimal bound. Our strategy to get near optimal cut size bound is as follows. First, we're just gonna partition node set into parts, something like n over a many parts, where a is some parameter that we cannot really control. It's just sum a. And what we know is that every part has size roughly at most a. Moreover, the cut size, which is like basically the number of edges crossing parts, like that cross between these parts here, it's gonna look like phi n times log of the number of parts. Not log n, but log of the number of parts. So this is like phi n log of n over a. Next, what we do is we're just gonna recurse on each part, vi. And the total cut size that we're gonna get for each part is gonna, by induction, be something like, for each part we pay something like phi a log n, but by induction this looks like phi vi times log vi. Now this sum looks like this. The total size of vi is just n, but each vi has size at most a, so this is log a. So the total cut size when you like sum them up, it looks like this. In this first level, we pay phi n log n over a. In the recursion, we pay phi n log a. In total, this gives you phi a log n. This is optimal. Okay, so this looks great, and this is our strategy. By the way, I want to mention that this factor here, in one recursion level, you can see that we still pay something like log n in the worst case. This log n is unavoidable because of flow cut gap. Yet, you can see that the total overhead when we sum over all recursion is still close to log n, because although this is at worst log n, we get some saving of n over log of n over a, and this sum, when we sum this and log a, it gives you log n. Okay, so that's the strategy. And in the reality, we're gonna pay something here, like you're gonna pay gamma, which is sub polylogarithmic bound sub-polylogarithmic factor throughout the whole recursion, but that's okay. Anyway, you can see that this step is really the key step, the partition step. Yeah. So let me talk a bit about it in high level. How does it work? The way that it works in the first step is just totally standard. Everyone use this when you use LP. We just solve the sparse cut LP. Once you solve it, it will give you a spreading metric on vertices. Okay. And now we're just gonna try to do some partitioning with respect to this metric L. Our inspiration is from the work by Bansal, Kurtsernik, and Schwartz, that they used some technique to get improvement on cut width approximation to something like log n from log to the 1.5. This technique is very simple but clever. It uses only some basic tools like greedy ball packing and bar towers partitioning, but it's really nice. Now what we do is to use some black box adaptation of this BKS paper. It needs to be not black box because we even solve different LP. So now for expert, very quickly, I want to mention that this is not the same as symmetric if you know it. Symmetric is a technique to improve overhead from log square to something like log n log n. It has been successful in many problems like feedback arc set and more. But the requirement, as far as I know, is that you need to use the same spreading metric when you recurse throughout the whole recursion. But in our setting, whenever we recurse, the spreading metric change completely. And that's why we need different trick. The technique that we use instead is BKS. Okay, now let me conclude. Again, we get expanded decomposition with near optimal trade-off. For cut version, it's the first polynomial time algorithm. For flow version, it's even the first existential result. The main open problem I want to mention is this. Is tree specifier by Recke, which can be viewed as a hierarchical version of expanded decomposition, which is even more powerful. It has a very similar state of the art, where with exponential time, you get near optimal bound of log n. And for polynomial time, for cut version and flow version, we get something worse by square root log or log factor. Now my question is, can we get some similar improvement like in this paper? That is, the conjecture is that you can get tree flow specifier with near logarithm quality in polytime. There are more open problems, like can you improve the running time to almost linear time? Or can you extend this work to vertex expander and directed expanded decomposition? That's quite likely that you can. So that concludes my talk. Thanks a lot.